Welcome to the Professor's DuBois channel. This is Professor Corey, and this video is a mini lecture based on our third lecture covering material from Chapter 4. This is in no way equivalent to our actual lecture where we discuss and practice the material in much more detail. In our previous lecture, we used our reactants to predict products, determine the states, and balance the complete molecular equation. The next step is to write a total ionic equation. For this, we must write everything that dissociates completely in water. To make this simple, we need to realize that only two things will ionize completely in water, and these are strong acids and soluble ionic compounds. There are only 6 strong acids, so these can be memorized. Ionic compounds need to be identified, and the solubility chart will be used to determine if they are soluble. In this equation, the only compound that does not dissociate is the calcium fluoride. It is ionic, but it is not soluble. Confirm this with your solubility chart. The result is the total ionic equation. Notice that the total ionic equation has ions that are identical on both the reactant and product side of the arrow. These are called spectator ions. They are present, but they do not contribute to the reaction. We will eliminate these by putting a line through them on both sides and writing the equation for the remaining species. This is the net ionic equation. Notice that the net ionic equation is balanced for both mass and charge. The importance of the net ionic equation is that these are the ions needed to produce solid calcium fluoride. The source of the ions does not have to be sodium fluoride and calcium chloride. We could use other soluble salts containing these ions. The net ionic equation shows what is driving the reaction. If we wanted a series of steps to follow, it would look something like this. To predict the products, we like to write the ions above the reactants and switch the cations. Once we have the products, we will cross out these ions as they are not part of the equation, but rather a visual aid for predicting products. You do not need to do this. The states are determined using the solubility chart because they are both ionic. Nickel sulfide is not soluble in water and labeled as a solid with the S. The only soluble ionic compounds and strong acids are written as ions. No acids here, but 3 of the compounds are soluble ionics. The spectator ions are the same on both sides of the equation, and the net ionic equation describes what remains. In some instances, each compound in the reaction is either a strong acid or a soluble ionic compound, and when this happens, every ion is a spectator. This is labeled as no reaction. For a reaction to occur, we need to form a pure solid, liquid, or a gas. Other drivers include dissolving of a solid. It is important to note that not every combination of compounds will react. We mentioned that many acid-base reactions, also called neutralization reactions, will produce water. This is a driver for the reaction because it produces a pure liquid. By the Bronsted-Lowry definition, an acid is a proton donor, while a base is a proton acceptor. It may be difficult to realize the hydrogen ion is a proton, but if you look at the subatomic particles, you will see that it is. Hydrogen has no neutrons, and if its one electron is removed, we are left with only one proton. The acid shown here is a special type of acid called an organic acid. We will often write the hydrogen in the front to help you identify it as an acid, but you may see it written with the hydrogen that is donated at the end, like it's written in red. In this reaction, the KOH takes the proton, so it is the base. The products are a salt and water. Remember that any ionic compound can be called a salt. This is a review of the 6 strong acids and a mention of strong bases by our definition. It's not 100% accurate, but it is useful for your current knowledge of chemistry and won't get you into too much trouble. Realize that bases are ionic compounds, so there is no mention of them in net ionic equations. We only break strong acids and soluble ionic compounds into ions. Weak acids and bases are soluble in water, so they are labeled aqueous, but they do not ionize very much, so we keep the compound together when writing the ionic equations. These terms are often used when describing acids, and you should be familiar with these terms. This shows the complete molecular equation and the total ionic equation for the reaction of a strong acid and a strong base. Pause the video and see if you can write the net ionic equation from the total ionic equation. The net ionic equation for the reaction of a strong acid and a strong base is always as written here. This is called a neutralization reaction because the resulting pH is neutral, or near 7. You should be able to follow along with this slide. I recommend trying this on your own, starting with just the reactants. Use this as your answer key. HF is a weak acid, so it is not written as ions. Gas-forming reactions will often produce enough gas that you can observe bubbles. Some gases like ammonia are very soluble in water, so bubbles will not be observed when we produce ammonia, but you may smell it. Window cleaners often contain ammonia for cleaning purposes, and the presence is easily detected by the odor. There are many gases, but the ones mentioned here are common in general chemistry, so you should memorize these so that you write the correct state when you are writing net ionic equations. These compounds decompose rapidly into gas and water, so if you do your double replacement and form one of these, put a line through it and write the products of the decomposition. These are all gas-forming reactions. Single replacement reactions can also produce a gas. These two examples demonstrate the production of hydrogen gas. Sometimes it is useful to write water as HOH when doing a replacement. In the first example, the potassium replaces the hydrogen from water to form potassium hydroxide, a soluble ionic compound that happens to be a strong base. The replaced hydrogen will grab a neighboring hydrogen to form the diatomic element. This would be a good time to refresh your memory on the diatomic elements if needed. Also notice in the second example that zinc solid and zinc ion are not the same and therefore are not spectator ions. Give this one a try and use the slide as a key. One of the products formed is H2CO3, so cross it out and replace it with CO2 and water. Another example for you to try. Again, we formed a product that decomposes rapidly. The steps involved in writing net ionic equations may seem like a lot to remember, but practicing these will improve your skills and confidence. My best advice is to remember that only strong acids and soluble ionic compounds are broken apart into ions for the ionic equations. Thanks for watching. Please give this video a thumbs up and subscribe if you would like to see more mini lectures on the Professor's DuBois channel.